So next, for challenges, you can read all the topics. One day we'll conduct one class for challenges or toppers. So in the last class, I was discussing this Bangalore South preparatory question paper. Part C, I have started in the part C, fourth main, first question completed, electric field due to superposition principle. One small mistake I did there, I corrected it. Very easiest that one. So next question that J is equal to sigma A derivation with usual symbols. So how to do that? J is equal to sigma into E. This is another macroscopic form of Ohm's law. If this question is not a came, they have not asked me this question means Ohm's law's direct statement and limitations they will ask either that one or this one they will come. So very important question for slow learners. I forgot there from the topic current electricity. What is this J? It is current density. Very important question for slow learners. Current density. So current density means it is denoted by the letter J. So that is equal to current per unit area of cross section. J is equal to I divided by A. Current per unit area of cross section is called as current density. Very important question for slow learners for 2 marks. Apart from this, mobility, drift velocity, and relaxation time is there. What is the SI unit then? For current, it is ampere. For area, it is meter square. Ampere per meter square, ampere per meter square, or ampere into meter to the power of minus 2 is the SI unit for current density. You can start this derivation from I is equal to current in a conductor, I is equal to NAEVD. So next you can take A to LHS, I divided by A, that is equal to what is left, N into E into drift velocity definition derivation, small letter E, capital letter E divided by M into tau. Tau means relaxation time. Small letter E, electrons, magnitude of charge of electron, capital letter E, electric field, mass of electron, tau means relaxation time. Now we know that I divided by A means it is current density J, that is equal to multiply all this N, small letter E into E square divided into capital letter E divided by M into tau. Now J is equal to sigma into E, directly you can write, where this sigma, the value of this sigma takes, where sigma is equal to N E square, where sigma is equal to N E square capital E divided by M. So this is called as conductivity. Conductivity, this sigma is called as conductivity. Here resistivity and conductivity, conductance and resistance, very important. I will discuss that also, very important within our just a fraction of second related to this. So this is the derivation. Just you can do this very simple steps. I is equal to NaEVD. From this equation you can start. I by A is called as current density J. So you can take the value of a drift velocity, substitute and simplify. Very important relation. This conductivity, resistivity, conductance and this resistance, just I will discuss that. Very important question. That's why. So first, resistivity is denoted by the letter rho. What is this resistivity? So it doesn't depends upon any dimensions. Independent of, sometimes to confuse you people, they will ask if length of the wire is increased twice, what will happen to resistivity? So resistivity will remains the same. It does not change. It doesn't depend on any dimensions. Resistivity or specific resistance. Two names are there. Resistivity or another name is specific. Other name specific resistance. Specific resistance. Other name specific resistance. So see how this equation to get this resistance. First, resistance of a conductor is directly proportional to length of the conductor. Resistance of the conductor is inversely proportional to area of the material of the conductor. So inversely proportional to area of the material of the conductor. Resistance, not resistivity. Combine these two equations. Now resistance is directly proportional to L divided by A. To remove this proportionality constant, we will use R is equal to rho L divided by A. The resistance depends upon length, directly proportional, inversely proportional to area. So R is equal to rho L divided by A, where this rho is called as resistivity or specific resistance. Simplify this equation. Rho is equal to, simplify this equation, rho is equal to RA divided by Ra divided by L. Then what is the SI for this specific resistance? Substitute the SI separately. For resistance, we know that ohm. For area, meter square divided by L meter. 1 meter square and meter will get cancelled. Ohm meter. Ohm meter is the SI for the specific resistance or resistivity. So very important equation. One problem definitely will come based on this specific resistance or resistivity. Very important problem. I will do it later. Then what is the definition for this specific resistance or resistivity? You can select some conditions when R is equal to, when R is equal to 1 meter, area is equal to when area is equal to 1 meter square, length is equal to 1 meter, length is equal to, when length is equal to 1 meter, R is equal to 1, area is equal to 1 meter square. Substitute here, rho is equal to R times of area is 1, length is also 1 meter square. So then rho is equal to capital letter R. According to this specific resistance, the resistivity can be defined as, it is the resistance of the material, resistance of the material of unit length and unit area of cross section. The conditions should satisfy. Resistivity is nothing but resistance of the material of unit length and unit area of cross section, that is called as resistivity, a specific resistance. Resistivity doesn't depends on any dimensions independent of length and area, but resistance depends upon or depends upon length and area, temperature also, other conditions. See, resistance is directly proportional to L in normal conditions. If the wire is melting and recasting, in 10th CBS it is there. If the wire is melting and recasting, for objectives, it will become useful for ATJ. R is directly proportional to L square. Length, resistance directly proportional to square of the length. So this is about resistance and resistivity. See, this conductivity and resistivity are inversely proportional. So conductivity and resistivity. So conductivity sigma is inversely proportional to rho. Sigma is inversely proportional to 1 divided by rho. Resistance is inversely proportional to 1 divided by G. Conductance. G is conductance. Resistance and conductance are inversely proportional. Resistivity and conductivity are inversely proportional. Okay. Next question. Next question. In the part C, fourth main. Next question. After this J is equal to sigma T, what is that? Mutual inductance. Factors affecting the mutual inductance. Terms you should explain. There I have explained in the J is equal to sigma E. J is current density. Sigma is conductance. E is electric field. A is area. Capital letter E is electric field. Tau is the relaxation time. Tau with usual notations. Next, mutual inductance. Factors affecting mutual inductance in the topic electromagnetic induction will come. Capital M is equal to mu naught mu r n1 n2 pi r square into L, pi r square into L, where with usual notations, mu naught means, what is this mu naught? Permeability. Mu naught is permeability. Permeability means the number of ability of the substance to allow the number of magnetic field lines. Very important question. In electrostatics, epsilon naught will come. Permittivity, that is permittivity, ability of the substance to allow the number of electric field lines there in first topic. Same definition, ability of the substance to allow the number of electric field lines there, but here ability of the substance to allow the number of magnetic field lines, electric field lines and magnetic field lines. Mu naught is permeability of, naught means nothing is there, permeability of free space, mu naught. Mu r, what is this mu r? R stands for relative, relative permeability. R stands for relative permeability. Mutual inductance means there should be two coils. So N1 means number of turns of the primary coil or first coil. Number of turns, number of turns of primary or primary coil, primary or secondary coil, wire, anything. N1. N2. What is this N2? Number of turns, number of turns in the, number of turns in the secondary coil, number of turns in the secondary coil. So R is radius of the coil. R is radius of coil and L is length of L is length of the coil. So mutual inductance, self-inductance. One day I will explain about only that EMI complete topic. I will explain mutual inductance, self-inductance. So SI unit is Henry for both mutual inductance and self-inductance. I think two marks question also. One question they have asked there in this previous main in the Bangalore South question paper only. So this is the equation mu naught n1 n2 pi r square and L. L will come A into L. I think in self inductance L will come here. It will come L here also, mutual inductance. Next question. Differences between dia and ferromagnetic material. In chemistry also it will come differences between dia and ferromagnetic and para ferro diamagnetic materials. L will come there. Next, differences between Farah and Ferro in Para, dia, Ferro, three are there, but in this question paper, they have asked about differences between the diamagnetic and ferromagnetic. So, diamagnetic and ferromagnetic. Dia and ferromagnetic. So, I will write some far away, Dudura. So, diamagnetic and ferromagnetic. Almost this ferro and ferra same. Next one more will come. The first one para. Para and ferro almost similarity is there, but that's why they have asked about these two dia and ferromagnetic. So here, so the magnetic materials acquire small magnetic moment in a direction. In diamagnetic materials, they will acquire small magnetic moment. They will acquire small magnetic moment. Not Mohan Mudugiri. Magnetic moment, small magnetic moment in a direction opposite to the applied in a direction opposite to the applied field, magnetic field, in a direction opposite to the applied field, magnetic field, that is called as diamagnetic materials. Next, ferromagnetic materials in the same direction, they will acquire magnetic moment. So ferromagnetic materials means not in a opposite direction. So in the same along the same direction or along the same direction the materials acquire magnetic moment. Diamagnetic materials acquire small magnetic moment in a direction opposite to the applied magnetic field, but these are will acquire the magnetic moment along the same direction of magnetic field. Along the same direction of magnetic field, they will acquire along the same direction of they will acquire magnetic field, magnetic moment. They will acquire magnetic. They will acquire magnetic moment along the same direction of magnetic field. Next, diamagnetic materials weakly repelled by a magnet. Whenever these diamagnetic materials are placed near a magnet, they will weakly repelled by a magnet. So, but these are strongly attracted by strong, not repel. So these ferromagnetic materials are strongly attracted by a magnet. These ferromagnetic materials strongly attracted by a magnet. Relative permeability mu r, relative permeability is less than 1, but here relative permeability is greater than 1 both for para and ferromagnetic materials. So some apart from this, you can give some examples and one more here. Magnetic field line that magnetic field lines are less crowded inside the material. Magnetic field lines are less crowded inside the material, but here magnetic field lines are more crowded inside the ferromagnetic material. These are the differences. Examples I will give. So diamagnetic materials acquire small magnetic moment in a direction opposite to the direction of applied magnetic field, but these will acquire magnetic moment along the same direction of applied magnetic field in the ferromagnetic materials. Diamagnetic materials weakly repelled by a magnet. These are strongly attracted by a magnet. Relative permeability is less than 1 for dia, greater than 1 for ferromagnetic materials. Magnetic fields are less crowded in a diamagnetic materials, more crowded in a ferromagnetic materials. Examples for diamagnetic materials, examples For diamagnetic materials, examples many are there. Bismuth, antimony, zinc, copper. For dia, we will write for diamagnetic materials. What are the examples? Bismuth, antimony, bismuth, antimony, zinc, copper, silver, zinc, copper, silver, nitrogen, H2 hydrogen, hydrogen, bismuth, antimony, water, alcohol, H2O, water, alcohol. These are all examples for diamagnetic materials. Whereas for ferromagnetic materials, nickel, nickel, cobalt, ferrite. These will use permanent and very important question related to this temporary and permanent magnets. For permanent magnets, they will use nickel, ferrite, cobalt, and iron also. Even iron also ferromagnetic materials. So these mainly ferromagnetic materials are useful for preparing permanent magnets. Permanent magnet means till lifelong they will retain as a permanent magnets. Temporary means, for example, best example solenoid. Only till the current flowing, until and unless where current will flows through the material, they will behave as a magnet. Once at the source, automatically the current stops flowing through the material. They will it will behave as a normal material only. For example, solenoid. Those are called as temporary magnets. Permanent and temporary magnets. Very important question, that one also. So next question. So after this this the differences between dia and paramagnetic materials. Very important question. It will come in chemistry, comes in chemistry also. Next question. So actually that question I confused it there. And the next question, mutual inductance, factors affecting the mutual inductance. The here magnetic field due to a long straight connecting of before this question, after that J is equal to sigma macroscopic form, ampere circuit line moving charges and magnetism it will come. Derive an expression for magnetic field due to a long straight conductor current carrying conductor. So you can consider one wire you can consider consider one straight line, one wire. So you can consider one Amperian loop or there Gaussian loop in electrostatics in applications of that uh, applications of Gauss law for hydrostatics. You can consider one point P. Let P be a point. At this point P, we are supposed to derive the expression for that magnetic field Amperian loop. This is at a distance. This point P is at a distance small letter r or small letter d. In some textbook they have taken it as a small letter d. From here to here the distance is small letter r. So this is Amperian loop, the imaginary surface. What is Amperian loop? Imaginary surface used to determine the value of magnetic field. Similarly, Gaussian loop in the first topic. What is Gaussian loop? Imaginary surface used to determine electric field there, but here magnetic field. So now we can use the Ampere circuital law. What is the Ampere circuital law? What it states that the line integral of magnetic field B into dl, that is equal to mu naught times of I, mu naught times of current passing through the conductor. Now B into this dl, that is equal to mu naught times of I. Now what is this dl? B is equal to, sorry, B into what is this dl? It is a Amperian loop, is a circular loop. Circular loop, we will take it as dl means integrate this dl, it will become integration of dl will become length. Length of one circle is 2 pi r, circumference of the circle. B into 2 pi r, that is equal to mu naught times of I. Very simple derivation. Now send this 2 pi r to RHS. It will become mu naught times of I divided by 2 pi r. This is the expression for magnetic field due to a long straight conductor, current carrying conductor. In some textbook they have taken it as a D. From here to here they denoted as D, but in almost NCRT, CBSE R only they have used, because here circle will come. Ampere loop is always a circular loop, imaginary surface to determine magnetic field. Just only 1, 2, 3, 4 steps, hardly 3 steps. This equation you can just remember, Ampere circuital law. So the line integral of magnetic field is a mu naught times of total current passing through the conductor. This diagram we can put and only 3 steps you can do. So this is the very small and very important derivation. Very small derivation, very important derivation. Next question. Principle of optical fiber. What is the principle of optical fiber and uses of optical fiber? So principle of optical fiber is we know that total internal reflection. It will come in the next part, second textbook. Very important TIR and conditions for total internal reflection. Very important question in 10th CBS also it is there. Very important questions. Total internal reflection in 10th CBSE also is there. 12th CBSE, 12th PU also. So optical fiber, one what principle it will work? Optical fiber TIR. TIR means total internal. TIR means total internal reflection. TIR means total internal reflection. So users, what are users? Mainly it is used for communication purpose only. What are the main users for communication purposes, for broadcasting, communication purposes, for broadcasting, and in industries, in army system, military industries, in army system they will use this optical fibers. Understood? Principal TIR mainly for communication and broadcasting in army and industries. In army system they will use these optical fibers. Next question. Bohr's atomic theory.